So let's start the second talk. Speaker is Srinivasan from Chennai Mathematical Institute, and his title is Either Semigroups on type 2 factors.
So it's a great pleasure to be here, and I mean it's not just pleasure for me. It's a very excited to be here. My long association with Sundar is not just intellectual; it's very emotional also. I mean he was my teacher, he was my PhD supervisor and a friend, colleague. And I mean some of the things he means for me, I mean he has done for me is something. Those equivalent of that has been done by people like who are very close to me, like my wife or something. Who was, the fact is very simple. If he was not there at some point of my life, I wouldn't be doing mathematics. So it's as simple as that. So it is. So I'm very happy to be here, and I thank Vijay for asking me to give this talk. So let me start. So it's a. So I'm going to talk about some objects called E0 semigroups and some other objects called 2-1 factors. And so I will define all those things. And this is a joint work with partly with Oliver T. Margath and with Sundar and with Panju Gopal. I'm presenting two works here. So before defining anything, let me give some introduction. It's R.T. Powers. He initiated this theory of E0 semigroups on both type 1 factor and type 2 1 factor. And so his first paper, the title is Index for Semigroup of Endomorphism on B of H. B of H means type 1 factor and type 2 1 factor. But then there has been a lot of development on the theory of E0 semigroups on type 1 factors, which is B of H, the bounded operator on all Hilbert, all bounded operators on a Hilbert space. So the basic problem in E0 semigroup is to provide examples and then distinguish them up to an identification called cocycle conjugacy. So in this context, Arvasan, he introduced, who has contributed enormously for this theory of E0 semigroups on type 1 factor. He introduced this notion of product system of Hilbert spaces, and he showed that it's a complete invariant. I mean it's a complete, so to study E0 semigroup, it's enough to study the product system associated with that, product system of Hilbert spaces. So he also defined an index for E0 semigroups on type 1 factors. So I'm talking about two objects. One is E0 semigroup and another is a factor. And I'm talking about types. There are different types of E0 semigroup. E0 semigroups are divided into three types, type 1, 2, 3, and factors are divided into three types, type 1, 2, 3, and as such there is no relation between them. So but I'm not going to talk about the types of E0 semigroup, different types of E0 semigroup in this talk. So just the point is on type 1 factors there are a lot of examples. Arvasan, using his index, he classified all these type 1 E0 semigroups on type 1 factors. Using this index, classifies them. And then there are more examples, more exotic, complicated examples of type 2 and type 3 have been constructed, and there is some progress, but we have to answer. So there are many questions regarding that are still not answered yet. So what we are going to talk about is E0 semigroups on a type 2 1 factors. On the contrast to the developments in type 1 factors, there is very little development on type 2 factors regarding the construction and classification of E0 semigroups of type 2 1 factors. So there is parallelly the product system of Hilbert spaces are kind of generalized to product system of Hilbert modules by Michael Skyde, Raja and Balaja Rambat and other people. But specifically a theory of E0 semigroups on type 2 1 factors, there is only one paper by Alexis Alavras. He proved this theorem. I mean he proved that actually I'm not able to see from here. So he proved that the E0 semigroups on type 2 1 factors are classified by their associated product system of Hilbert modules, an analog of Arvasan result. It's not exactly analog of Arvasan results. Arvasan result is much more deeper. I mean the result is he defines product system abstractly and shows that there is always an E0 semigroup associated with the product system of Hilbert spaces. Here it's not like that. If you have a E0 semigroup of type 2 1 factor, you can associate a concrete product system, and the E0 semigroups are cocycle conjugate, which I am going to define. Are cocycle conjugate, then the product system, if and only if the product system are isomorphic. So Arvasan also, so Alavras also defines an index for through something called boundary representation, but he shows that the boundary representation is invariant under conjugacy, which I am going to define, but that it's not clear whether that boundary representation is a cocycle conjugacy invariant. So in particular, whether this, I mean, this index he defines through this boundary representation, so it's not clear whether that index is a cocycle conjugacy invariant. In particular, there is a fundamental E0 semigroup on the, I mean, something called Clifford flow, which is defined on the, this is a most simplest 2-1 factor, which is hyperfinite 2-1 factor, and this Clifford flows, whether they are distinguished by this index, even though they have different index according to, I mean, whatever his definition was, they have different index, it is not clear, I mean, it's not proved that they are, I mean, they are different up to this identification of cocycle conjugacy. So let me, I mean, so we are going to talk about, I'm going to in the end, I'm going to say that these Clifford flows are in fact different through some other technique. So let us start, I mean, so let me start with the real mathematics. So for us, always H is always a separable Hilbert space. By B of H, I mean the star algebra of all bounded operators on H. So by a von Neumann algebra, I am not going to use this topology, but I mean, it's on B of H there is a norm topology, and there are several, so that's a very strong topology. There are several locally convex topology, and one of them is a sigma weak topology, which is actually the weak star topology. B of H is dual space. It's a dual space, it's dual of trace class operators, and so the sigma weak topology is nothing but the weak star topology on B of H given the pre-dual, the trace class operators. And something is a factor, we call a von Neumann algebra as a factor if the only operator which commutes with all of M is scalars. So in a von Neumann algebra will always contain identity scalars, and here, I mean, so they are the only operator which commutes, I mean, of course the scalars commutes with the scalar times identity, commutes with every operator, and if that is, they are the only operators, then we call that as a factor. And so we are going to, so in this talk we are going to talk about this particular factor called 2-1 factor. And this 2-1 factor is a factor which is infinite dimensional. I mean, there are other definitions. This is, I'm just using the equivalent definition for this talk. A 2-1 factor is an infinite dimensional factor. It's an infinite dimensional object, but it admits a finite trace. So the definition of a trace is this. It's just a positive linear functional. It's a linear functional from M to C, which satisfies this property. Tau of xy is tau of yx for all xy, and its important property is tau of 1 is 1. This is the finiteness. So it's an infinite dimensional object which satisfies some finiteness property. So here is a definition of E0 semigroups. An E0 semigroup on any von Neumann algebra is a semigroup of normal, unital, star, endomorphism, which are sigma weakly continuous. So I have to explain all these terms. All these terms are explained here. So it's on a von Neumann algebra M, and it's a collection of one parameter family of linear operators on M, and it's a semigroup. I mean, so alpha s times alpha t, when you compose you should get alpha s plus t, and it's an endomorphism, and that is, it preserves the products, it preserves the star, the adjoints in, I mean, our M is not, I mean, it's a concrete von Neumann algebra sitting inside B of H, so the adjoint is same as the adjoint for operators, and it takes the identity to identity. This is the identity operator. By one I mean the identity operator, and we need a continuity. When you fix a t, all this alpha t is sigma weakly continuous. As I said, sigma weak topology is just the weak star topology, and further we need, when you fix it x, the t going to this, I mean, so this is actually sigma weakly continuous, that's what I have written. So this is the lower star is the pre-dual of this. So it is a t going to rho of alpha tx when rho, I'm sorry, this should be rho, sorry, this I have written x, this should be rho. Okay, this is a mistake. So when rho comes from this pre-dual, then t going to this is the complex valued function that has to be continuous. So it's just for definition. I mean, I'm not going to prove anything, so I mean, I'm not going to show any proof of anything, so this is not, I mean, we are not going to use this. So let me give examples of E0 semigroup. To give example, let me fix this. I'm going to give two examples, and this is something I'm going to use I'm going to use these things in common for both the examples, so let me fix that. So KB, for me, small k is a real Hilbert space. I take a real Hilbert space, and this KC, by say k superscript c is the complexification of the real Hilbert space. And TT, I'm going to use ST for something else. Usually this will be denoted by ST, so because I'm going to use ST for something else, I call this TT. TT is the shift semigroup. This is a unilateral shift on L2 0 infinity k defined by this. I mean, you take any function f in L2 0 infinity, then TTF of the function at any point s, I mean s plus t is going to be the value at s, I mean value at f of, I mean value at S for the function f. Okay, it just shifts the function f. So this is a well-known operators. This is a semigroup of operators. It's well known that it's semigroup and they are continued. There is a continuity in T, strongly continuous. They are all isometries. Okay, so I am going to use this. I am using this semigroup of operators in L20 infinity. We are going to get a E0 semigroup. So here is the fundamental example of E0 semigroups on a 2-1 factor. So as before, I take this K. K is that Hilbert space I have already talked about. Then I am taking this L20 infinity functions. I mean, so maybe this is all square integrable function taking values in K. Okay. So I consider H to be the antisymmetric Fock space of this. So I don't want to define antisymmetric Fock space. I mean, this is some sort of exponentiation. This is, I mean, there are different ways of exponentiating a Hilbert space. This is one such thing, and H is a antisymmetric Fock space of this L20 infinity Kc. And so in the antisymmetric Fock space, there is something called a vacuum vector. I mean, it will be, so that vacuum vector I am denoting by omega. Then and the antisymmetric Fock space, these are all what are called creation operators. So if you have on omega, it takes omega to f, and it takes anything. I mean, so there are these finite particle vectors. It just attaches. I mean, but this is the antisymmetric tensor, not the usual tensor. It attaches a f to the left of any finite particle vector or any vector like that. So these are all bounded operators. I mean, in symmetric Fock space, this won't be bounded operator. So because it's antisymmetric Fock space, this will be bounded operator. So we have defined this A star f, then you take the adjoint, which is AF. Then we define this U of f to be just the average of these two functions. So I am taking, remember, I am taking f from this real Hilbert space. So this U of f will be a self-adjoint operator. So these self-adjoint operators, in fact, they will be self-adjoint unitary, I think, or at least constant times unitary. So they will satisfy this relation. This commutation relation, UF, UG, UF will be the inner product between f and g times 1. So if f and g are orthogonal, they will anti-commute, for example. This is the anti-commutation relation. So they will satisfy this relation. And if you take the phenomenon algebra generated by this UF, okay, so that is the hyperfinite 2-1 factor. I mean, it's a well-known. There is only one such hyperfinite 2-1 factor. It's isomorphic to that hyperfinite 2-1 factor. And I mean, it's in standard form. I will talk about it later anyway. So it is. I mean, this M sitting in B of this H is in standard form. Okay, so I will talk about the standard form later after some 2-3 slides. That's because I want to define this for, I mean, I want this to be self-adjoint, and I mean, yeah. So I mean, I have to say that this UF, if you evaluate on omega, that will give this. I mean, the product of UF that will give the trace. So my E0 semigroup is defined. I mean, so I want to define the E0 semigroup on M. And so I define on this U of f. I mean this. So beta, the E0 semigroup beta t defined on U of f is U of TTF. So using this TT, I define this beta t. And this, I mean, this is of course defined on the generators. And the fact is, it will extend to a unique E0 semigroup. Of course, it has to be unique because UF generates M, and this extends to a unique E0 semigroup from M. So similar thing we can do on a free Fock space. So let H be a free Fock space. I take the same L20 infinity Kc. So I mean, this complexification I take because I mean Fock spaces are defined for complex Hilbert space. So I take this H be the free Fock space and omega be the vacuum vector again. There's a vacuum vector in free Fock space. Then for F, so again this is same as the same creation operator, except that it's not anti-symmetric tensor. It is just the usual tensor. So I define L of f is the left creation operator, so which takes the vacuum vector to f, and any other orthogonal to vacuum vector, it just attaches a f on the left. Full Fock, yeah, that's free Fock, yeah, full Fock. So the phenomenon algebra generated by this SF is just the average of LF and LF star. That's well known that it's isomorphic to the free group subfactor. I mean the free group subfactor with infinite generators, which is F infinity. So it's isomorphic to that. and again M is in standard form. We can again define the same, I mean in a similar way we can define an E0 semigroup alpha T of S of F is S of TTF for all F in this. It is defined on the generators and it will extend to a E0 semigroup on the full, I mean on this F in L of A, on this M. Okay, so now still I haven't, so I have defined E0 semigroup, I have given two examples, two families of examples, and there are many more families actually. So then I want to talk about, I mean now I want to say what I have been talking about, the identification within E0 semigroups. So to define this identification, the identification is what is called the cocycle conjugacy, which I want to define. To define that, first I define what a cocycle is. A cocycle is, I mean, so if you have alpha is an E0 semigroup from M, then a cocycle for an E0 semigroup is a collection of unitary operators which satisfies this cocycle identity. That is just all US, alpha S, if you just compose them you get US plus T, which is just the cocycle identity. It's a cocycle for alpha S. Then if you have a cocycle, then you can define a alpha U, a perturbation of alpha T like this, which will again be which is again a E0 semigroup. The cocycle property will ensure that this is also a E0 semigroup, I mean which is also, it is also a semigroup. So when we say two E0 semigroup alpha on M and beta on, I should have put it respectively. If you have two E0 semigroups on N and M and M, I mean alpha and beta respectively on M and N, then alpha, we say alpha and beta are conjugate if there is an isomorphism between them which interjoins these two E0 semigroups. So if there is an isomorphism between M to N which satisfies this relation, if you pull it back and act alpha T and apply theta on that, then you should get beta T. So we say something is cocycle conjugate, they are not actually conjugate, alpha is conjugate to a cocycle perturbation of that. That is beta, alpha, beta are cocycle conjugate. If there exists a cocycle like that, then you can form this perturbation, and beta is conjugate to alpha U. So this is cocycle conjugate. So we want to classify, I mean classifying up to conjugacy is beyond question, so it's too difficult. So we talk about cocycle conjugacy. So from here onwards, I am going to talk about, that's for, I mean all these things, the cocycle conjugacy can be defined for general von Neumann algebra. So here onwards we fix M is a type 2-1 factor. I mean we have only two examples. So one is hyperfinite 2-1 factor, one is a free group factor. Then we assume that M is in the standard, this is what I said as standard form. M is contained in B of L2 M tau. What it means is, by definition, I defined by a 2-1 factor, it has a trace, and using the trace you can define an inner product on that. Okay, it's I mean the inner product between any two x and y in M is tau of x star y, and that will give an inner product. You complete that M with respect to that inner product. That is what is this L2M, which is a Hilbert space, and M will act on this L2M by left multiplication, and that's what I mean by M is contained in that. So this is like I mean see, functions on, I mean on L2, on any L2 the continuous functions will act. So, I mean this is not exactly like that. L infinity can act. So it's something very similar to that. So there is an identity function here, identity operator in M. So that is what, so that will sit inside this L2 M tau as a vector, and that vector I call as omega. So that is the cyclic and separating vector. I mean if you know JNS construction, this is exactly the JNS construction with respect to the tau. So this is what I call a standard form for a 2-1 factor. So now I define a operator. So now I have alpha T. Alpha T is an E0 semigroup acting on M. Now I define a ST, and this is an operator on L2M. Okay, this is the Hilbert space operator. That is an endomorphism. Alpha, it is an endomorphism. I define a Hilbert space operator ST, where ST acting on any x omega. By x omega, I mean this L2M tau consists of basically M. M is contained in that, and that sits as M omega. Okay, I call this x omega is basically the x here. Okay, x or x hat or something. So ST x omega acting on this alpha T, ST acts on this x omega, I mean ST takes x omega to alpha T x omega. Okay. Since the trace is unique, using the trace, uniqueness of trace or something, one can verify that this is ST is actually an isometry and it satisfies this relation. One can verify that this relation is satisfied. So this relation is what is called ST satisfying, any operator satisfying this relation is what is called a unit. And I am defining unit here. So, but this unit, this particular unit, this is special because it is defined like this using this representation. So, this particular unit we call as the canonical unit or a vacuum unit associated with this alpha. And this ST is invariant under conjugacy, but it's need not be invariant under cocycle conjugacy. So there may be other units, ST is a unit, there may be other units, and so a unit for an alpha, for this E0 semigroup alpha is a family of semigroup. I mean, so it's important that this satisfies two property. One is it has to be a semigroup, Okay, it's a semi-group. I mean, TS, TT is TS plus T. It's a semi-group of operators, and it satisfies some continuity condition. That is what the strong continuity I mean. So, and it satisfies this intertwining property. TTX equal to alpha TX TT. I mean, I have just written it the other way. It's the same thing. Alpha TX TT is same as TTX. Okay, it satisfies for all x in M. It satisfies this for all T. This is satisfied. So, this is what is called a unit for an alpha. And the collection of unit I denote by U alpha, which is one can prove that this is actually a cocycle conjugacy invariant. I mean, one need to, I mean, if you have a cocycle, then you can left multiply a unit to get a unit for the other one. So, it's well known that it's a cocycle conjugacy invariant. So, given an E0 semigroup, I have defined some unit, and unit is one cocycle conjugacy. I mean, we want to distinguish, we want invariants for E0 semigroup, and the units are one such invariants. There is another invariant. This is what is called gauge cocycle. I mean, there is cocycle I have already defined. A gauge cocycle is a local cocycle. I mean, it's a cocycle which satisfies this condition. Of course, by our definition, cocycle has to be in M, and it has to commute with by this I mean commutant. Okay, by this it commutes with the range of commutes with all alpha Tx for every x in M. So that's what I mean by this. It's in the commutant of this for all T. So then this G alpha we denote by the, I mean, the G alpha is all gauge cocycles. So one can show that this G alpha forms a group with respect to multiplication. I mean, you can compose two unitary operators. I mean, each ut, if you have ut vt, then you can compose ut and vt, you get another wt equal to ut vt. That gives another, that's again a gauge cocycle. So it's a and star will give the inverse. So it's a group under usual group operation, and this group is again a cocycle conjugacy invariant. You can show that this is also a cocycle conjugacy invariant for alpha. So we have got two cocycle conjugacy invariant, and we would like to compute it for our examples. So before talking about, I mean, I will come back to this unit and cocycle, I mean, gauge cocycles again. So before that, I want to talk about, I want to define. So given I have a M, which is a 2-1 factor, which is sitting inside B of H, where H is our L2M. Then I want to say I want to define something called a dual E0 semigroup. I want to define on the commutant. There is a natural way of doing it. So if we have this, so this is 2-1 factor. So you can also, there is a Tomita-Takasaki theory. If you don't know Tomita-Takasaki theory, it's all right. You can always define this operator x omega going to x star omega, which will in this case, when it is 2-1 factor, in this case it will be a, it's not a linear operator, it's a conjugate linear operator, but it will be anti-unitary. So what is called an anti-unitary? It's a unit, it will satisfy the unitary property, it will be a j square, I mean j star will be j, so it will be a anti-unitary on this L2M. So using that anti-unitary add of j will take M to M commutant, and M, I mean it will be given a opposite isomorphism between M and M commutant. So using that opposite isomorphism, I can define an alpha t prime on M prime. M prime is the commutant of M. So I define this alpha t prime x prime as alpha t, I mean this will bring, this x prime is in M prime. So this j x prime j will bring it to M. I apply alpha t and then take it back to M prime. So this gives an opposite E0 semigroup or complementary E0 semigroup or dual E0 semigroup, whatever one wants to call. So given a E0 semigroup on given a E0 semigroup on M, I have defined an E0 semigroup on M commutant. So I define something called a munit or a multi-unit for an E0 semigroup alpha by, I mean this is some operator TT, which is a unit for both alpha and alpha prime. I call it as a multi-unit. Okay? It should be a unit for both of them. So the collection of all munits or multi-units is a cocycle, one can show that it's a cocycle conjugacy invariant. It's not very clear actually. I mean, in the sense that, I mean, it's people who are working on E0 semigroup, it's clear that units are cocycle conjugacy invariant. So here this proves that it's actually a cocycle conjugacy invariant. The point is, if ut is a cocycle and if you have alpha, this alpha prime is also a cocycle conjugacy invariant. We can define this u prime and that will be a cocycle for that, and the prime for this alpha u will be alpha prime perturbed by this u prime. Okay. So this alpha prime, whatever we do, that's a cocycle conjugate, that's invariant under cocycle perturbation. So this, then we have this, you can, I mean, usually this, the units are preserved, I mean the correspondence between units for the cocycle conjugacy to E0 semigroup with our cocycle conjugate is by multiplying by the cocycle, but here we do it by ut prime. So that will give again a multi-unit, and you get, so the multi-unit is a cocycle conjugacy invariant for that. The collection of multi-units is a cocycle conjugacy invariant. So if we have two units xt yt, so I was calling ut tt, so if you have xt yt, two units, you can take this xt star yt this will, so first this will xt star yt, because it's a unit, it will commute with m. I mean, this intertwines alpha t and identity. So this will intertwine identity and alpha t. So this will intertwine. This will be in the, this xt star yt will commute with m. And since it's a unit for m prime also, I mean alpha prime and m prime also, it will commute with m prime also. Since m and m prime generates the b of h, it will commute with whole b of h, so it will be a scalar. So xt star yt is a scalar, but since because of the multiplicative property, it has to be e power something, it will be multiplicative, so that's why I get this e power something. There I get a constant. This is a scalar which depends on this xt and yt, that's what I have called. It's e power ct, that c depends on xt and yt, so xt yt is equal to e power ct xt 1. Times 1, it's a scalar. So we, given any two units, we get this scalar which is called the covariance function. So we get a function from this u alpha, so this is the collection of all multi units. We get a function from here to here, and which is I mean there is a condition called, it's a conditionally positive definite, and when we have a conditionally positive definite function like this, we can construct a Hilbert space. It's well known that one can construct the Hilbert space. I don't want to go through that. So the dimension of the Hilbert space, I call that as an index for alpha. Okay, the dimension of that Hilbert space, and this index is of course a cocycle conjugate invariant, but then this is not the index defined by all of us, as we will see. I mean, as I will show that this is not same as the index of alpha. So now we have a different question. So now we have defined an index for E0 semigroup. Now we have a different question. The question is, suppose if we have this alpha t, we have, I mean, so we have alpha on m prime and alpha prime on m prime. So does there exist a E0 semigroup alpha 2 on this b of h such that it restricts to alpha on m and alpha prime on m prime? So in case such a E0 semigroup alpha 2 exists on this b of h, we say that this alpha is extendable, and in that case this index is nothing but the power Sarvasan index, which is already defined, which is the index of this alpha 2. Okay. So here is the, so some, I was talking about gauge cocycles. This is something about the gauge cocycles. If we have two gauge cocycles, then we can associate a scalar, I mean, within that, I mean, for that cocycle. This is not clear for any, I mean, this is in, I mean, this is a particular case of 2-1 factor. Okay, it's not, we have the trace, because of the trace we can prove this remarkable identity like this. So it satisfies this trace. If you apply trace on this, it satisfies this identity. So because of that, I mean, you can embed these cocycles into units by applying on vacuum vectors, then applying the trace you will get this. So this satisfies this identity. Because of that, we can be given any two ut star tau t by applying trace, we can get this scalars. So again, this scalars is again conditionally positive definite, and we can construct a Hilbert space called H alpha. We call this in Hilbert space H alpha, and this H alpha as a dimension, of course, and that dimension we call it as the gauge index. So we have defined two kinds of index. One is the index through coming from multi units, which is the unit for both alpha and alpha prime. Now using this G alpha, we can define an index, which is this gauge index. So one would like to compute these two index for our specific examples, and so here is the result. So I mean, I'm just saying that these two index are not useful. So after doing all the computations, we find that these two index are not actually useful. So that's what I'm just saying. So this doesn't actually distinguish those E0 semigroups. Well, this is a long computation. I mean, in the sense that so in antisymmetric Fock space, it's not easy to compute the units. So using stochastic integration, we can actually associate for any units are multiplicative. Units I will talk about it later. If you have a unitary cocycle, you can associate. I mean that's in bijection. There is a bijective map between unitary cocycles and unitary cocycles and multiplicative cocycles. They are multiplicative cocycles and additive cocycles. Using that, we can compute the additive cocycles, and one can prove using some computation, which I am not showing here. One can prove that there is only one multiplicative identity is the only multiplicative cocycle there. So that will imply that the dimension, the gauge dimension is 0. I will show the index is 0. I mean, I'm going to show. I'm going to give a reason why the index is also 0. So in the case of free flow, we haven't calculated the index yet. The index coming from multi units, but we can calculate again using the same idea of this additive cocycles, etc. We can show that the gauge index is again 0 here. So it's just, I'm just saying that So I mean, this is, of course, it is important to calculate these indexes and other things. It's an important invariant. I am just saying that these two indexes are not actually useful. So this shows that it's not, this index is not same as Halavera's index. Halavera's index is n for Clifford flow, yeah, infinity for free flow. So I mean, I didn't talk about this, so it's not same as that. But that's not cocycle conjugate invariant. So that's the problem with that. So now, so how to show that Clifford flows are in fact are different with respect to this cocycle conjugate invariant. So let's so again let M be a 2-1 factor and it sits in a standard way. Then I can define this ET. So ET is all intertwiners in L2M, B of L2M, which satisfies this relation. I mean, for unit, I said there is an intertwining property. Further, it has to be a unit. It has to be a semigroup also. Here, I am not. There is no condition like that. It is all such T. Given I fix a T. I take all operators in B of H, which intertwines alpha T and the identity representation. So, okay, it just satisfies the relation. And similarly, I define something for alpha T prime like this. Then I take the intersection of HT is the intersection of these two things. Okay, ET intersection ET prime. So this forms, I haven't defined what a product system is. This HT frames, so I haven't defined the super product system also. The HT forms what is called a super product system. Well, what a product system is, you have this family for each ET. Actually, this will form what is called a product system of Hilbert modules, M prime Hilbert module. This will form what is called a product M Hilbert modules. And I mean, I don't want to go into that language. So, but these are all Hilbert spaces, HT are Hilbert spaces. I mean, because if you take something here, then if you have T and S in this HT, because it is in T star S will be in M commutant as well as in M. So, I mean, as I have already talked about it for units. So, it will give an inner product on this HT. So, HT is a Hilbert space, but it won't form a product system. The product system in the sense, a product system is something, if you take HS tensor HT, there is a unitary map, there is a well-defined unitary map from HS tensor HT to HS plus T. So, in this case, we won't have a unitary map, we will have an isometry map. So, here at this point, I have to say that, I mean, Rajaram Bhatt and Mithun, they have done something called inclusive system, which is something which is the opposite of this. There one has the isometry from HS plus T to HS tensor HT. Here we have an isometry from HS tensor HT to HS plus T. So, it's the other way. So, this Kostler called this a super product system. So, I am calling this a super product system. That is called a sub product system or something. So, this HT will form a super product system and it is of course a cocycle conjugacy invariant for this alpha. So, this is something we have shown. I mean, this ET which is defined through intertwiners, which actually this is not strongly closed when ST is not when ST is not a unitary, which is just an isometry. So, in that case, this is not actually strongly closed. If you take the strong closure of MST, that will give ET prime. If you take the strong closure of this, that will give ET. So, this is just I am stating. This is used in the proof of that, but I am not. I mean, this is not relevant for the talk when I am not going to prove anything. So, here is this condition. We talked about extendability. I mean, extendability means we have alpha on M. So, then we can define an alpha prime on M prime. So, then this alpha prime that can be extended to something on the whole of B of H. So, we talked about that extendability. If there is a E0 semigroup on whole of B of H, which restricts to alpha and alpha prime on M and M prime respectively. So, this is the equivalent condition for the extendability. Alpha is extendable if and only if alpha Tm and alpha T prime M prime, this generates a factor. I mean, this is the range of alpha T, this is the range of alpha T prime. They together should generate a factor. Or, so this is a easier condition. This is difficult to check whether something is a factor, but this is also not so easy anyway. So, I use this condition. So, I mean, to prove something, I use this condition. So, this set is this is a set. I mean, this is X coming from commutant of these two ranges, and Y coming from M. Then we can so omega is fixed. Then we can apply X alpha T Y omega. Then that is a total set in H. So, this is equivalent to saying that something is extendable. Or the another equivalent condition is HT actually forms a product system. In fact, HT, if it forms a product system, it will be the product system corresponding to that extended E0 semigroup. So, for Clifford flow, we have computed this HT. This HT, we can explicitly compute this HT. Well, I mean, this is HT can be identified. HT is a space of operators. Here I am talking about something vectors. I mean, this is well known that these vectors can be realized as operators, some sort of shift operators. So, this HT is nothing but I have put a 2n here. So, this is all even particles. I mean, this is all even even particle space. See, antisymmetric Fock space contains both finite particles. It's just the subspace generated by the even particle vectors. That is exactly this HT for this Clifford flow. So that would imply that this is not a product system. This won't form a product system, because if you take HS tensor HT, that HS plus T, the range will be of generated by vectors of foreign length. I mean, it's not generated by if we. So I am extremely sorry. This has to be T. It's not L20 T. That is L20T. Sorry. Yeah, I didn't notice. This is HT is L20T. Okay. I'm sorry about that. So I think I don't have time to explain how this operator comes through, but this you can apply this. I mean, this tensor product is defined through the chip, and this won't actually form a product system. So that would imply that Clifford flow of any rank. I mean, we expected that this should be extendable. This will in fact extend to the car flow. There is something called car flow. We thought this will extend to car flow. The point is it doesn't extend. So this is a shock. So nasty shock actually. So this doesn't extend. So then we can show that using this whatever the super product system, we can show that if Clifford flow of rank n, I haven't said what is rank, there is a Hilbert space small k, the dimension of that Hilbert space is the rank. Okay. So if Clifford flow of rank n is not cocycle conjugate to Clifford flow of rank m if n is not equal to m. This we can, I mean, if suppose, if they are cocycle conjugate, then the super product system has to be isomorphic. But if they are isomorphic, then we can show that so there is this L2K, then we can talk about all products. We get, there is a product system you can associate to this super product system. If they are isomorphic, then one can do something and show that the product system is also isomorphic. Okay. One has to do some calculations. One can show that they are isomorphic. That will imply that the car flow of rank n is isomorphic to cocycle conjugate to car flow of rank m. So which is not true. So this is not true. So that is the proof. So all these Clifford flow are not cocycle conjugate to each other. So this is the proof. And we still don't know about free flow, but there is something we can show using Alavara's result. So one can do the same thing again. So there is this. You can take all these even products of this U. There should be a bracket here. UF1 up to UF2n. This our hyperfinite 2-1 factor sitting inside operators on this antisymmetric Fock space. They are generated by these UFs. But if you take only even products, that will form that's also isomorphic. You take the phenomenal algebra generated by that will also be isomorphic to hyperfinite 2-1 factor. But then then you can restrict this Clifford flow to that subfactor. That will give another, that we can call that as even Clifford flows. So one can do the same thing, the same kind of thing. Then you can show that the even Clifford flows are not cocycle conjugate within themselves for different m and n. And also one can show that this I use Alavara's proof. I don't see, the point is if I can prove, the even Clifford flows are not cocycle conjugate the original Clifford flows. So the proof is, the point is, so we got this HT which is generated by these even tensors, even antisymmetric tensors, that doesn't have a unit. There is only one unit for this. One can prove that doesn't have a unit. So it has only one unit. So there has to be a vacuum unit. So in this case, when there is only one unit, the boundary representation of Alavara's will be a cocycle conjugacy invariant, because that's conjugacy invariant. So unit will be taken to it has to. There is no other choice. So but then both these even car flows and even Clifford flows and this Clifford flows, they have only one unit. So boundary representation is in fact a conjugacy representation. So using Alavara's has proved that they have different boundary. They have same left boundary representation, but not the right boundary representation are different. So he has proved that. So using that, one can prove that these even Clifford flows are not cocycle conjugate to the original Clifford flows. So that's all. Thank you.
So any question or comments?
Yeah. Because you are no, because the units we define on standard representation. So we have to. So we use only standard representation because all these modules, it's not coming from. All these intertwiners are not coming from M. They are coming from B of L to M. So one has to fix this representation. The commutant has to be fixed. Everything has to be fixed. So we have to use standard representation. Otherwise, we have to use a different theory. This certainly won't work. This depends on the standard representation. So.
Can one distinguish what kind of 2-1 factors by the
I don't know. I mean, the E0 semigroup, even automorphism is not understood well. So I don't know whether, I don't think so. But there are factors where it doesn't allow E0 semigroups. I mean, so E0 semigroup means it has a subfactor of infinite index. So I mean, some questions like that can be answered, but I don't think a E0 semigroup can determine. I don't know. I mean, so at least it's not developed. The theory is not developed yet.
Question, comment? If there is no, then let's understand.
Thank you.